All right, welcome back. We are Game 2005. That's Game Physics in the fall 2020 semester at George Brown, and we're week 4, part 1 of our broadcast, and we're going to talk today about laws of motion. Before we get there, what I want to do is I want to go up on our content area, and hopefully we can put in a video link, right? I'd like to try and do that, a YouTube video, as I'm letting people in. And share the YouTube video that I have. If you want to watch this video again, and if you have accessibility issues and you want to have things like closed captioning on and so on, there's real-time closed captioning you can get from within YouTube. It's not terribly accurate, but it's better than nothing. So I think it's a good way of watching. A lot of times you can always go back, and what you can do with that is you can fast forward me if you have to, or rewind a little bit as you go back and watch this thing through YouTube. All right, so that's up on Blackboard now. If you look at that Blackboard area, let's take a look at this week and what we're doing. So we're sitting at week 4, and like I said, the plan was this week you were supposed to get lesson or assignment 2, but I gave you assignment 1 last week. So what we've done is we've shifted these 2 assignments down. So next week, week 5, you'll be getting assignment 2. Assignment 2 will be due in 2 weeks from then. So it'll be due week 7, the same time as your midterm test. Again, your midterm test is a theoretical test that's going to happen in the first half. It's going to cover everything from week 1 to week 7, and it's going to be in the format of true, false, multiple choice. If you figure that if I take at least 10 questions from each of these weeks, and this is including questions like calculation questions, things that you've seen in the back of the PowerPoints are good questions that I can ask you that are relatable to physics. Those kinds of questions may be on your test, so please watch out for those things. Okay, of course it'll be open book, and you'll get 2 attempts and you'll get the best attempt out of 2. Okay, so this is the theoretical test that you're going to get, which is coming up in your midterm in a few short weeks. So again, if you haven't had a chance to do some of the homework in the back of the PowerPoints, there's some example questions. I recommend you go through them and try and figure them out. They'll help you greatly in understanding what to do on the test. Okay. Also during lab, I think that Spencer now has posted some things to help you on your assignment 1, and as well as understanding some questions, some basic physics. Did you guys find, so show of hands, do you guys find this week's tutorial helpful? I'd like to try and give some, sorry, I meant check marks. Check marks, if you can put a check mark that yes, you found tutorials helpful, or you need something else for the tutorial as an X, as an example. Can you show me a show of like any kind of response or feedback? I'm seeing some check marks. Juan says no. Or sorry, yes, Kira says no. Kira, you want to come on the mic, or maybe kind of instead of on the mic because you're being recorded, you want to kind of put something in text and talk about what we could have done differently for you. I mean the lab, yeah, the lab. When I say tutorial, I mean lab. It's very slow. So do you mean it was very slow for you because you know how to do stuff, or his pacing was too slow for you? How did you find that? Okay, I'll bring that back to him. Thank you for that. Too much time to fail. Okay, thank you for that. Can I get how about Alexander Barnes there? Can you put some stuff in the chat there if you want to talk about what made your experience less than optimal? I'm just going to thank you for that feedback, by the way, guys. Yeah. I'm just kind of listening to this. So, okay, so late start. All right, thank you for that. I'll take that back. So part of it, I think, for people who are watching, there's some YouTube links, and again, a late start for some of the tutorials, maybe a little bit too slow. And how about did he cover things about to help you with the assignment? That's what I'm hoping that you guys got help on the assignment to try and start working towards your assignment number 1. And again, I'm looking for check marks, please, if you kind of understand what to do with your assignment, and X if you have no clue. Only the physics calculations. Okay. You're more struggling with the code. Okay, so thank you for that. So again, what I'm hearing is you could have probably used more code help and less calculations help. I mean, it's a kind of a balance, guys. Because remember, the calculations that I'm talking about in our lecture are going to be on your test. So it's important that you guys get that too. And that's why when we had a discussion, Spencer and I had a discussion this week. I just want to make sure that you get the right kind of help from his labs, and because he can do whatever you want. Direct him. If you're looking for help, talk to Spencer about what you're looking for. Ping him on Discord if you can. Ask him questions. Say, look, Professor, can we get, we want to do this work in our lab this week. Can you help us out with whatever the thing that you're looking help with? And he's pretty flexible in terms of producing content. He's very good at what he does. Right. So make sure you ask him what he wants. Again, I asked him I said, I would like them to have more help on their test. And, as well as some of the stuff we've talked about in lab, in lecture. Sammy should. Yeah, I mean, I've shared the template with him, so he's looked at it before. I'm not sure, if he's got as much familiarity as I do or Alex has, because Alex and I developed it. But like I said, if I have time later on, I'll try and help you guys out with it near the end. Okay? Worst case scenario. You never use the SDL template. Yeah, that would be bad, Vincent. Hopefully we can do a little tutorial on how to do that. And maybe what I can do is I'll talk to him about it for the next thing. It's just that there's got to be a balance between using the template and answering the physics questions. And that's this is the challenge with this course. This course here has both. You have physics questions and you have SDL. Okay, let's see what we can do. Let's get on with this, though. I want to talk about more of this as we go forward. Okay, so last time we talked about motion in 1 and 2 directions, right? And this time around, like it says here, so first we talked about geometry in the first week, then motion 1 and 2 directions, and now finally we're into laws of motion. This is kind of getting into the good stuff. Why? Because once you get into laws of motion, you start to create a more realistic scenario in terms of the way things move in your physics engine, the little thing that you're making. Okay. So again, when we describe an object's motion and we describe its position, we talked about this before, velocity and acceleration. Those three aspects of an object's motions are really important. And I think if I was going to program this in SDL, definitely what we talk about when we talk about physics in game programming is really about rigid body dynamics, right? Rigid body dynamics is the main thing, and collision detection. Those two things are super important in terms of when we think about physics. So when I think about rigid body dynamics, I'm thinking about position, velocity, and acceleration, as well as collision boundaries. Okay, so that's kind of the first part. Sorry, I just got some late joiners here. I'm adding in right now. By the way, for those people who are, when I'm being distracting, going back and forth, it's because in this case, every time someone enters the room, I have to physically admit them on my own. All right, which is part of the security aspects that they've added into to Zoom lately. Okay, so. Two main factors are the things that we're going to be looking at as of this point on. One of them is something called forces that are acting on an object, and the mass of an object. All right. So forces and mass are required when we talk about the laws of motion, and I'm talking about the Newtonian laws of motion. And by the way, most of our physics engines, because they're concerned with rigid body dynamics and collision detection, mostly use Newtonian laws of physics for their simulations. Okay, I'm not saying that they all do, but most of them do. So Sir Isaac Newton, famous physicist, 1642 to 1727. He formulated the basic laws of mechanics. He discovered, and I like to say that, the law of universal gravitation. All right, and he also invented a form of calculus, lots of observations dealing with light and optics as well. All right. By the way, does anyone know off the top of their head, what is the gravitational constant of the universe? Does anyone know? Don't look it up. Does anyone off the top of their head what it is? Can you put it in the chat? And what does that mean? It's not 42. The gravitational constant of the universe. I know. Wouldn't it be nice? Yeah, the universe. There is a gravitational constant of the universe. Take a look at the gravitational constant for those people who don't know, right? By the way, I'll give you the number since you guys aren't coming up with it. It's an actual number. It's 6.67 times 10 to the negative 11. That is the gravitational constant of the universe, right? And that's something that was developed out of the law of universal gravitation that Newton came up with all those many years ago. Why do we need the gravitational constant of the universe? Well, when we describe two bodies, and we'll talk about this maybe later on, and I want to describe the gravitational effect, right? Or I want to calculate the gravity that a body might have, and I'm talking about a large body like a planet or a moon. I can use the mass of that body plus the gravitational constant of the universe to calculate its gravitational pull or the acceleration due to gravity at the surface. Okay, that's what we can do with it, which is really cool. So 6.67 times 10 to the negative 11. That's the one, Kira. Yeah. All right, let's continue. So forces. Let's talk about forces. Again, forces are used to push and pull objects throughout the entire day. All right, we can use forces to throw a ball or kick a ball. We can push an object and so on. So forces are what Newton's laws kind of work around, the three laws of motion that we're going to talk about, right? And again, they've been extended. Newton's laws were extended as we learn more about physics, right? But we're going to work primarily this week with Newton's laws. And a force is something in your mind, when you think about the word force, it causes acceleration. All right? It causes acceleration. Let's continue. So here's some forces. Constant forces or contact forces, like, for example, springs. There's something called spring forces, right? There's kicking forces. There's forces, for example, that have to do with friction. So forces of friction, forces of resistance, for example, things like air resistance, which is a different kind of friction, right? There's field forces. So example, gravity is considered a field force. There's also nuclear forces between two objects and magnetic forces. So different kind of forces that play in the real world. Question for you is, do we really care about every kind of force? Well, we do care about gravitational forces between two objects. Electromagnetic forces, typically in a game, we don't really care too much about them, right? Electric charges. Typically, we don't do that unless you're making that kind of game. Nuclear forces between subatomic particles, that's also a force. We aren't really concerned with it, remember? Weak forces. So things like radioactive decay processes and all that kind of stuff, these are all examples of field forces. The main one we care about is gravitational force. And like I said last week, we really don't know still what gravity really is. We don't have a graviton particle. We just can feel the force. We can observe gravity, but we can't actually detect it in any way. Okay? So that's the important thing to note. There's other kinds of forces as well. For example, the forces of a spring. We can calibrate the magnitude of a force using a spring as well. How much can a force exert from a pushing perspective or a pulling perspective? We can use springs to help us measure forces. Forces are usually described as vectors because forces have both a magnitude and a direction. And usually forces are used perpendicularly relative to each other, which means at right angles to, right? A perpendicular force, right? So example, if I'm pulling an object up, right, then it's usually perpendicular from the center of gravity, all right? Typically, that's how we do it, okay? So there's perpendicular, usually is what we think about when we look about forces. Wow, people are still coming in late. And here's an example of a couple of forces. So we talked about forces are, what we do is we use some kind of measure. So here's an example, a spring in this diagram. And we can see that in this example, a downward force, F1, elongates the spring by 1 centimeter, right? Whereas another downward force, F2, elongates the spring by 2 centimeters. We can still say then, observationally, that the first force, right, is weaker than the second force in a downward direction, okay? If you apply F1 and F2 together, we can add them together, just like vectors. So if I have a vector for F1, and if I have a vector for F2, and they're pointing in the same direction, we can add both those vectors together to get a total displacement of 3 centimeters. So the forces can add together. Again, this is all things being equal. Okay? If we have forces in different directions, we can calculate the distance between the two forces, and this is what we're going to do a lot, right? When we can use Pythagorean theorem and Euclidean mechanics to pull things in the, kind of the diagonal direction. So example, if I have a force 2 that's acting to the right and a force 1 that's acting down, then I'm going to get a final force, F, that's acting at a particular angle that is relative to this vector, these two vectors together. So it's going to make a triangular it's going to go in a different direction is what I'm saying. And this is going to be used with the sum of all forces being put together. Let's talk about Newton's first law, okay? So the first law, when we think about it, right, is if an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration, right? And this is called the law of inertia, all right, law of inertia, and it defines a special set of references called inertial frames. And we can call this inertial frame of reference, but really when we summarize Newton's first law, and if I was going to skip the inertial frames idea, right, the alternative statement is, an object at rest tends to stay at rest. An object in motion tends to stay in motion. That is Newton's first law. Okay? So here's how you can restate it. In the absence of external forces, when viewed from an inertial reference frame, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity. It's more accurate, right? That applies to everything nowadays, from philosophy to all kinds of actual physical observations we can make. So in other words, we can say, you see a lot of commercials like that where they say an object at rest tends to stay at rest, and they talk about a person. The person is an object. And an object in motion tends to stay in motion, right? In other words, if you're active, you're going to keep active. If you're not active, you're going to stay on the couch. I want you to remember that, though, because what's happening is that means a motion, an object, is not going to move spontaneously on its own unless it's pushed, right? Unless it's pushed or pulled or some kind of a force is applied to the object, it's going to stay where it is. And if it's in motion, unless a force is acting on the object, is going to still stay in motion. And a good example of that is the microgravity of space, right? We have less gravity affecting objects in space than we do here on Earth, especially the farther they out from a planetary body, right? If an object is in space and is flowing in the same direction, when there's an insignificant amount of gravity pulling it towards a gravity well, that object will continue to go in the same direction perpetually, forever, with very little slowdown. Sure, it can slow down over time because there's still going to be some micro amounts of friction as it might encounter things like gas and dust in space, but the theory is that it's going to keep going forever, right? Whereas if an object's inside of a planetary body, it's going to fall. If it's lifted up high, it's going to fall down, and when it hits the Earth, it's going to stay there until it's moved again by another force. Okay? So again, when you think about this Newton's first law, the body is not going to move the particle that we're talking about is not going to move unless a force is applied to it. Okay, that's Newton's first law. And the first law also allows this definition of force as that which causes a change in the motion of an object. So there's no force unless the motion of an object has altered. So here's a thing about that. If I apply a lot of force on an object, but it doesn't move, then the net force is zero. Right? That's the thing that happens. So we can kind of measure force that way as well. When it comes to inertia and mass, right, the tendency of an object to resist any attempt to change its velocity is called inertia. So in other words, if I'm already in motion, right, and there's something that's causing me to stop or slow down, we can say that I have inertia. I have enough inertia, right, that I'm going to keep moving in the same direction. Same thing is if the object is at rest, it's going to take energy for me, force, to move that object and to start motion. Okay? Mass is that property of an object that specifies how much resistance an object exhibits to change its velocity. And this is really, really important. In other words, if a mass, an object, is sitting on the ground and I've got to push it, the more massive an object is, the more energy it's going to take for me to push it or change its velocity. Right? When we say mass, I don't mean weight. I mean a number of particles or components that make up that object. So what I mean is, the denser an object can be, right, it can have the same mass, as an example, as you. Let's say there's two masses, a human and some kind of cube. They have the same amount of molecules. Both the cube and the human have the exact same amount of molecules or particles that make up that object. For the most part, they're going to have the exact same mass. Mass is a matter of matter, the amount of matter that they've made up with. All right? If the matter is compressed into a smaller object, it's not going to be more massive. It will be equally as heavy as an object as in Earth's gravity, as an object of similar mass that has a bigger volume. So volume doesn't necessarily make the mass. Mass is a factor of how many particles make up an object. Okay? Good example of this is a neutron star, right? A neutron star could be considered to be very, very small, right? Or something close to a singularity. A singularity in physics might be something that is really, really small, maybe a small particle, or it might even look like a billiard ball or smaller, right? That can have the mass of a sun inside that small space. The more mass that's inside of a space that's smaller, the more we say that it changes the space-time continuum. All right. In other words, it has an effect on the geometry of space itself around it, and in fact has more gravity. More mass equates to more gravity. If I had the mass of the sun and I took the mass of the sun and I compressed it down into the space of a human being, that human being would potentially sink through the earth and do bad things to it, as an example, if it had that much mass. In fact, the earth would probably collapse onto itself if there was something that massive in that small of a space, right? So think about how it would warp reality if you had something like that big. I'm just being extreme here when I'm talking, but I want you to get the idea that more mass is usually more particles. And the denser an object is packed, the more apparent weight it has according to its volume. Okay. And we can say that depending on the masses, how many masses can be defined in terms of accelerations produced by a given force in terms of acting on them, right? The magnitude of the acceleration acting on an object is inversely proportional to its mass, inversely proportional, right? So the more massive an object is, the less acceleration is going to affect it to get it to go, right? We can say that mass is a scalar quantity because there is no direction for mass. It's not like mass is going to give you I'm looking at mass as a directed quantity. Mass is something that is concentrated in a specific spot, and the unit of measure for mass that we're going to use in this course is kilograms. Okay? Sometimes if you get pounds, in a question. You need to convert it with our equations to work. You should convert it to kilograms, or you should have both the quantity, the size, your distance calculation should be both in meters and kilograms, or in pounds and feet. Go with one metric system, right? Whether it's imperial or metric, one measurement system. But for mass, for us, it's going to be in kilograms. We can say that mass and weight are different. Weight is a perceived kind of quantity, if you will. And it's changing. It's going to change according to the gravity of the environment that it's in. Mass stays constant. So mass is a constant quantity, right, for the most part. Right? We tend to gain and lose mass. That's as humans, as an example. The Earth usually loses mass. The Sun is constantly losing mass. It's not gaining mass. It's losing mass slowly, over millions of years. It's going to continue to lose mass as it sheds more of its components out into the universe, right? And if you think about it, any expenditure of energy is a conversion of mass into energy. And the more efficient the conversion, the less things like smoke and heat and other effects of that conversion are evident. So when we convert mass, if I can convert mass into energy, right? And this is what happens with the sun. Mass, when it gets converted, if it's not perfectly converted, you have it converts in terms of we have side effects in terms of heat and smoke, typically, when we have something like that. Yes, and that's true too. As the sun loses mass, it will continue to get bigger. Why? Because the ability, its gravity is going to change, and the ability for it to retain the shape that it has is going to warp a little bit. But that's something else. That's something in when we talk about astrophysics, and this is not the content of our course. However, it's very interesting for people who care. So when I look at mass and weight, then, if I take a look at my mass on Earth, it's 2 kilograms. My mass on the moon, also 2 kilograms. My apparent weight on Earth might be 180 pounds, right? I'm using pounds here as opposed to kilograms. And my apparent weight on the moon might be only 30 pounds. Why? Because the moon has 1/6 of Earth's gravity. So therefore, my mass is moving towards the center of the moon with less acceleration. There's less force being exerted on the same amount of mass, right, on this other environment, from this other environment. So if you think about that, if I'm in another planet, and if I'm in a heavy gravity world that has twice the gravity, 2Gs as an example, compared to Earth's 1G, 1 gravity, 9.8 meters per second. So twice the gravity, let's say 20 meters per second, right? Therefore, our apparent weight would double, given that our mass would stay the same. Okay? So mass and weight are different. I want you to remember that. A lot of the physics stuff that we're going to be doing is going to be done with mass, not weight. Newton's second law. Okay. And there's a relationship. Newton's second law states that there's a relationship between force, mass, and acceleration. When viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Okay? Better stated, force is equal to mass times acceleration. Okay, that's what it means. And F is equal to ma. That's a summary, a nice summary for Newton's second law. Force is equal to mass times acceleration. Once we have that ratio, F is equal to ma, then we can describe many types of motions. When we think about mass and acceleration, and we think about forces, we think about net forces. The sum of all forces is what this is saying right here. Okay? The sum of all forces. The sum of all forces are all the forces working in 3 dimensions. Now we're working in the third dimension. We don't care so much about x and only x and y, but we're also thinking about the z direction. Okay, so the sum of all forces in all directions, right, is what's acting to get is what's going to be happening when it comes to calculating mass times acceleration. So our acceleration is a vector 3 object, if you think about it, right, in the real world. Now we can cut it down if we're working on a 2D game like you guys are working on. As an example for this course, some kind of 2D simulation, right? We only care about the x and y coordinates. And for a lot of the work we're going to be doing here in this course, we're only going to be thinking about x and y accelerations, okay? To make it easier. Not that we couldn't think of the z acceleration quantity, right? But only because adding a third dimension makes it like 6 times more difficult to calculate things sometimes, and much longer calculations. Okay, but the same principles can be applied in the third dimension. So when we think about total force then, the sum of all forces, we have to break down our forces into component forces on the x-axis and on the y-axis. When we think about the units of force, we use something called newtons. All right, and that's something you should think about. So, and newtons also equate to kilograms per meter squared. Okay, per meter squared per second squared, per meter second squared. Kilogram meters per second squared. Sorry if I say it properly. So kilogram meters per second squared is another way of using newtons, but we use newtons because that's just a much easier measure. Okay, but this idea of kilogram meters per second squared, where do we get this? Well, kilogram meters, mass, right? And then the distance or displacement is in meters for every second. Meters per second squared is the acceleration. Meters per second squared, acceleration, right? Kilogram meters per second squared is the way we would figure this out. But we want to use newtons because it's easier. Also, you might think of another way I found funny, which was 1 slug foot per second squared. 1 slug foot. I like that. And one thing to look at it is 1 Newton is approximately equal to a quarter pound of force. A quarter pounder. All right. So here's a Newton's second law example. A hockey puck having a mass of 0.3 kilograms slides on the frictionless surface horizontally on a rink, on an ice rink, right? 2 hockey sticks strike the puck simultaneously, exerting the force on the puck, right? The force F1 has a magnitude of 5 newtons, this one. Remember? Quarter pound of force for every newton. So it means like we're looking at 2.5 pounds of force going, or quarter pound, sorry. That's 1.25 pounds of force going in this F1 direction, approximately. And is directed in with a theta, an angle of 20 degrees below the x-axis. Okay, this way. And the force F2 has a magnitude of 8 newtons, right? And is directed with a theta of 60 degrees above the x-axis. Notice that these two angles form, a total angle of 80 degrees. Can we use Pythagorean theorem to figure out between kind of the total force, as an example, when we add these two vectors together? Can we use Pythagorean theorem for this? The answer is we cannot use Pythagorean theorem because it's not a 90-degree angle, right? We'd have to use other calculations for this, right? Pythagorean theorem, right? If we think about this as 80 degrees, then these two angles here have to equal to 100 degrees, right? If you kind of put together the triangle. So we want to determine, here's the question, determine both the magnitude and direction of the puck's acceleration. Magnitude and direction, okay? So how would you approach this problem? Well, let's think about the way we would do it. We conceptualize. The acceleration of the puck will be in the same direction, right? Because both sticks are hitting it at the same time. Remember, what we want to do is we want to calculate the sum of all forces. What are the sum of all forces? How can we calculate these things? Categorize. Because we can determine a net force and we want an acceleration, this problem is categorized as one that may be solved using Newton's second law. Force is equal to ma. Analyze. Let's try and put this in within a formula. The sum of all forces on the x-axis, we break it down into component forces, like we said, is equal to force 1 on the x-axis plus force 2 on the x-axis is equal to force 1 cos theta plus force 2 cos phi. Why? Well, now we get back to our motion in two directions formulas from last week, right? If I had velocity, and if I want to break down the components of velocity across different x and y axes. Remember I told you, when we think x-axis and an angle, I'm thinking about cos something. If I think y-axis and an angle, I'm thinking about, typically, sine something, okay? So when I break down the component forces, think about the forces as energy, right? I want to take, when I look at force 1 and force 2, I want to take force 1 cos theta, almost like I did velocity, velocity 1 cos theta, and I want to add those two things together, all right? When I want to get the sum of all forces, right, as an example, right, I get these two formulas, and then what is acceleration across the x-axis, right? Well, we know that force is equal to ma. Force is equal to ma. And what I want is, I want to isolate acceleration because that is what the question is asking, right? It says, determine the magnitude and direction of the puck's acceleration. Magnitude and direction. Magnitude is the number, direction is the angle. These two things describe a vector, an acceleration vector. We can't get the acceleration vector until we break it down into its component forces. So the way it works is, if force across the x-axis is equal to F1 cos theta plus F2 cos theta, we take this and multiply it by its mass, right? So, we divide it by its mass because the ratio is force is equal to mass times acceleration. So if we were going to put equals to mass times acceleration on the right side, we would have that force 1 plus force 2 is equal to mass times acceleration. If we rewrite this thing, we're going to get something that looks like this. The sum of all forces on the x-axis over mass, which works out to be F1 cos theta plus F2 cos phi over the mass. That's equal to the acceleration on the x-axis. And then we can do the same thing for the acceleration on the y-axis. Taking it further, we sub in our numbers. We look at 5 newtons of acceleration as an example, because we said 5 newtons of acceleration on the x-axis. Cos theta is minus 20. Why minus 20? Because it's below the x-axis. Because the angle is below the x-axis, we're going to apply a negative sign to it. Anything above the x-axis is going to have a positive sign to it. Negative 20. Plus 8 newtons across the x-axis for the other force, right? When we divide it from this across its mass, we get an acceleration on the x-axis of 29 meters per second squared. We get an acceleration on the y-axis when we do the same substitution. Again, I'll move in there as 17 meters per second squared. To get the total acceleration, now we know we can use Pythagorean theorem, because now we have everything in terms of our vectors, right? So we can say that then we want to take the acceleration across the x-axis squared plus the acceleration across the y-axis squared, and then get the square root of that, which will give us the final acceleration, which works out to be 34 meters per second squared. That is the magnitude of the acceleration. When we want to find the angle of the acceleration, we want to take the angle across the y-axis and the angle across the x-axis. So the tangent is what we're doing here. And we're going to get the arc tangent. And this is going to be, we're going to get this back a lot of times on the computer in radians. We want to convert this from radians to degrees to give us a total angle of 31 degrees, right, relative to the x-axis, which means in the positive x direction. So this is an example of how we'd use to find out the two puck question or two stick question. Questions around this. So again, all we're doing is using F is equal to ma, that formula, and breaking it down component-wise or member-wise, if we want to talk about it from a vector perspective in C++. Okay. Yes, we use Pythagorean because we have acceleration on both the x and y axis. And we're calculating, if you think about this, we're calculating the next pixel in this case, if you're looking at it from a game perspective. The next pixel, where we're going to move our particle to the next pixel. Okay, let's think about gravitational force now, right? So we know that Newton's second law is force is equal to ma. Gravitational force then could be labeled as force of gravity, right? Gravitational force, which is the force that the Earth exerts on an object. If we had force of the moon, right? Force of gravity on the moon, FGM, then it would be the force that the moon exerts on an object if we're on the moon. Here, we're just using the force of gravity. Because the force of gravity can be described as G, right? The force of gravity, right? That's the acceleration due to gravity. We can change with the formula a little bit. Instead of using F is equal to ma, force of gravity is equal to mass times gravity, instead of mass times acceleration. This is also something we want to use a lot. And notice it says weight. When we talk about weight, it's the force of gravity, which is equal to mass times gravity. Your mass times gravity is your apparent weight in kilograms. Okay? And usually we do it in newtons. How much weight does something have in newtons? We can talk about mass times gravity. So anytime we ask for weight, the weight of an object is, 30 newtons. Well, we can find out what its mass is because we know what gravity of Earth is. Okay? More about weight. Because it is dependent on gravity, weight varies depending on the location. Again, it really depends on if we're closer to the planet's surface or if we're farther away. Again, on a rough estimate, 1 kilogram is roughly equal to 2.2 pounds, as an example, as it's approaching the Earth's surface. Farther out, the apparent mass or the apparent weight might be lower. Okay, because we're farther away. Remember that thing that I asked earlier? What is the gravitational constant of the universe? The gravitational theory, the gravitational formula, takes the gravitational constant of the universe and also calculates the distance between the two masses to figure out the force of gravity. Okay, so the farther an object is, you use the gravitational constant of the universe between that mass and the mass of the body that's attracting it, and then you can find out the apparent, the total gravity between those two things. And there is a difference between the mass. So Newton's law is the mass is the inertial mass and measures the resistance to change. This is an important one. The resistance to change in an object's motion. All right, that's important. So the more massive an object has, and from a Newton's law's perspective, the more resistance to change it has. Okay? And it says, experiments show that gravitational mass and inertial mass have the same value. All right. And I don't know why this one's messed up, but we're going to fix it because I don't know if I like the way it's looking. And this one should just be moved down in here. Don't know why. Anyways. Who knows? Maybe it was the conversion. Newton's third law. If two objects interact, the force F12 between object 1 and 2 exerted by object 1 and object 2 is equal in magnitude and opposite in direction to the force F21 from object 2 to object 1 exerted by 2 on 1. And for example, F12 is equal to negative F21. How do you say this in a nicer way? For every action, there is an opposite and equal reaction. That is Newton's third law. Every action has an opposite and equal reaction. So, in other words, when I have a collision, when we talk about collision response, I'm going to have an opposite and equal reaction in the opposite direction, typically. Now, with collision response, we also have a loss of energy. The loss of energy, whenever two objects collide, right, we have a loss of energy because energy is expended. When we create things like noise, sound is energy. We're actually converting our inertia into sound. When we do that, the louder a sound is, that's energy loss. There's also loss in terms of heat, right? And because of the friction that two objects have when they hit each other, right? So you're going to have energy loss whenever where two objects collide. So you're not going to have 100% energy firing back in the opposite direction. Okay? And we're going to talk about later on in this course when we talk about collision response. But for the most part, with the stuff we're talking about with Newton's laws, for every action, there is an equal and opposite reaction. So simply stated now, we've learned 3 laws of motion. An object at rest tends to stay at rest. An object in motion tends to stay at motion. F is equal to ma. There's, mass and acceleration are in, the effect of mass and acceleration on force are inversely proportional. That's what it means. And then Newton's third law is, for every action, there is an equal and opposite reaction. Okay? And that's what we put in here. One of the forces is the action force. The other is the reaction force. Right? It doesn't matter which is considered the action and which is the reaction. They are both equivalent forces. The action and reaction forces must act on different objects and be of the same type. Here's an action-reaction example. Number 1. The force F12 from 1 to 2, right? Exerted by an object 1 on 2 is equal in magnitude and opposite in direction to force F1 for F2, 1. Exerted by object F2 on object 1. Now notice that these objects have different masses. So, if the amount of force exerted on both objects are the same, right, it's going to have an effect on when they collide, which object moves. Because remember, objects want to stay at rest or stay in the same direction, right? They keep moving in the same direction by Newton's first law, right? So what's going to happen is when these things collide and the third law is going to take place, this object here, number 1, is going to move in the opposite direction. But because of the weight, or the mass of object 2, object 1 is going to move back, the other way more than object 2 is going to move back along its initial path. They're going to collide and move in the opposite directions. But you're going to see a little bit more motion towards object 1, and depending on how massive object 2 is, you might not even see much of a reaction as object 2 barrels through object 1. Okay? And we'll talk about that. One thing we got to talk about when we talk about Newton's third law is something called the normal force. Okay, the normal force. The normal force is the reaction of the force the monitor, in this case, exerts on the table, right? And usually it means perpendicular in this case. And the action, the earth on the monitor, right? Well, what's happening is, with the normal force, the table is acting in the equal and opposite direction to the weight, to the mass, the acceleration due to gravity on the monitor through the table. Now, because the monitor is not falling through the table, we can say that the table is counteracting the force of gravity on the monitor equally. In other words, our normal force is equal to the force times the gravity. Right? Those two forces are equal. Why? Because we can say here that the monitor is in equilibrium. Right? It's not falling through the table. And because the monitor is not falling through the table, we have to say that the normal force and the force of the gravity that's acting on the monitor are equal. If it wasn't true, if the force of gravity was greater than the table could sustain on the monitor would fall through the table, or the table would collapse. Okay? But that's not the case in this picture. The case is the monitor is being supported by the table, which means that the minimum normal force, if you will, on the monitor is equal to the force of gravity. Okay? So we're going to talk about normal force later on too. When we talk about forces on an object, a lot of times it helps because we want to talk about the sum of all forces. We want to talk about a free body diagram. The free body diagram treats objects like they're particles, and we draw vector arrows in the directions of the forces. All right? So example, in the normal force would act in an upward direction. and the force of gravity would act in the downward direction. These two arrows would be the same size because the object is in equilibrium. It's not moving, right? And there's no lateral forces in any way. We don't have somebody pushing the monitor, and there's no phantom telekinesis that's going to take the monitor off the table, right? So therefore we can say that this object is in equilibrium. When we draw a free body diagram, we draw it just like this. We draw the mass, the center of mass, as a point, like this, and we draw arrows in the directions of the forces. In this case, the normal force and the force of gravity. We're going to use the particle model again as we talk about objects when it comes to the laws of motion. When we use analysis models, one of the things that we're going to do is, for the most part, unless otherwise stated, we would ideally use frictionless surfaces. Frictionless surfaces are easier to deal with because friction is an opposing force, right? When we think about the sum of all forces and we think about friction, friction acts against a force, especially when an object which is resisting motion. If it's on the ground, it's resisting motion. It has a static friction that has to be overcome before it starts to move. We're going to talk about that later on. The other thing that we want to talk about is this idea of the tension. Tension forces are going to be equivalent. If, for example, if I'm using a rope or some kind of pulling mechanism, right? Even my arm, and the force of tension, we can say, on that body, right? Like, let's say a rope or a chain or my arm, right? If I'm going to pull an object or I'm going to move an object, whether I'm pushing or pulling, right? The force of tension, we can say, is going to be at least equivalent, right, to the inertia that object already has, what already possesses, which means if I'm pulling an object, if I'm holding an object, as an example, off of the ground, my arm has to be able to sustain a tension of a certain amount of force. If it can't sustain the tension, either I'm going to drop the object, right, as an example, or my arm could be affected. I could get hurt, as an example, if I continue to try and hold on to it. Easier to look at it from a rope. If I have a rope and I have a rope connected to a mass, if the tension is greater than the tensile strength of the rope will snap, right? And if the rope snaps, the object will fall. It'll escape. It will not be in equilibrium anymore. So there's some assumptions. If the acceleration of an object that can be modeled as a particle is 0, the object is said to be in equilibrium, which is what we said about the monitor and the table, right? In other words, the sum of all forces across that particular axis would be 0. Okay? In this case, it means that the sum of all forces on the x-axis and the sum of all forces on the y-axis would both be 0 for an object to be in equilibrium, mathematically. Here's an example of an equilibrium problem. Okay? Yes, I am definitely pantomiming now. Yes, thank you for that. So, a lamp is suspended from a chain of negligible mass. Notice it says negligible mass. We want to make it so that it's insignificant, we're going to say, okay? The forces acting on the lamp are the downward force of gravity and the upward tension in the chain. Why? Because the tension is holding the mass of the lamp from falling, right? The tension on the chain is got to be equivalent to the force of gravity, right? If it's not, we can say that the lamp would fall, right? The chain would snap and the lamp would fall, right? So the tension must be the same as the force of gravity or greater. Usually it's greater, right? If an object that can be modeled as a particle experiences an acceleration, there must be non-zero net force acting on it. In other words, you can't be in equilibrium if the thing is moving, right? If an object is moving, there must be force acting on it, and force in some ways equates to acceleration. Force and acceleration are on this, they're kind of, there's a direct proportion, right? If I have force, it must mean that I have acceleration. Why? Force is equal to ma by Newton's second law. If my acceleration was 0, that means I would have 0 force. Now that's counterintuitive for us from a real world perspective. We may think that there's force being done, right? Example, you push against a wall. Go push on a wall right now, right? You're exerting energy, right? Unless you're moving the wall in any way, any material way, if you're not moving that wall, we can say that the amount of force, the net force exerted on that wall by you is 0. 0, right? So the first thing is we want to draw a free body diagram and apply Newton's second law in component form. So here's an example for tension. A tension, here's another thing. A tension acting through a rope is the magnitude of the force of tension. So this is the magnitude of the rope. We would draw a free body diagram with an arrow along the same side of the rope. Notice that they've drawn it very carefully here as an example, and it looks like the free body diagram is being drawn to the right as an example, right? And whereas you see there's two other forces. One that's moving with the force of gravity pulling down, and it's counteracting normal force going up. We can say that the y force, the sum of all forces across the y-axis, are in equilibrium. Do we really care about them? If we assume that the friction is a frictionless surface, somehow this man or this person here that's being described can pull this object and there's no friction, right, if we say, or the friction is being accounted for in this net force to the right, so he's overcoming friction with some kind of positive vector to the right, then all we care about is the forces across the x-axis in this case. But the force across the x-axis has to be, or the tensile strength of the rope has to be at least equivalent in the other direction, right, as an example, to the force of that he's exerting, or this person is exerting on the mass. Otherwise, if the tension on the rope, the tensile strength of the rope was less, the rope would snap. But we can draw a free body diagram that looks like this because this is the sum of the forces going to the right. We can apply Newton's second law, and we can see that sum of all forces on the x-axis is equal to the tension, which is equal to mass times acceleration only on the x-axis, right? The sum of all forces on the y-axis, though, is we take the normal force minus the force of gravity, right, which is equal to 0, okay? Why? Because we know that on the y-axis, he's not sinking through the ground. Therefore, on the y-axis, the sum of all forces are known to be at equilibrium. A note about normal force. The normal force is not always, it says, equal to the gravitational force of the object. For example, in this case, right, the sum of all forces across the y-axis is in equilibrium, and the normal force is equal to the force of gravity times the mass, the weight, basically, plus the force I'm exerting on the book if I'm pressing down. However, if I can't push the book through the surface that is supporting it, we can say that the normal force is greater than my combined force that I'm pushing down plus the force of gravity acting on the book. Okay? So the normal force is at least equal to or greater, and we can think about it as equal to because the book still remains in equilibrium. If it was greater, if the normal force somehow was greater, the book would fly up. It's not flying up, right? So the surface does not present forces that push up beyond the forces that are pushing down upon it. That is kind of a characteristic of the normal force. So the first thing we should always do is draw a diagram. So first, draw a diagram. Choose some kind of convenient coordinate system. I highly recommend this. If you can make it look positive instead of negative, flip it around. For example, if I say the object is traveling to the left, as an example, making the object travel to the right, to make your calculations, and then flipping the signs later might be an easier way to calculate things. Why? Because to the right is positive and to the left is negative, right? And usually dealing with negative signs makes things more challenging to look at. All right, and the next thing is categorize. Is the model or particle in equilibrium? Yes or no? If it is, then the sum of all forces is equal to 0. Is the model or particle under a net force? Is there motion? Is there acceleration? If there is, then the sum of all forces cannot be equal to 0. Then we draw a free body diagram for each object, right? Include only forces acting on the object. Find components along the coordinate axes, right? Be sure the units are consistent, meters, kilograms for everything. Apply the appropriate equations in component form. Solve for the unknowns, right? And then finalize, check your results for consistency with the free body diagram and make sure it makes sense. That's another one. It doesn't say that here, but more or less it means make sure that this thing makes sense, right? Like, think about what it means in the real world. Does it make sense? If it doesn't make sense to you in the real world, something when you check on it, something's wrong. You've calculated it wrong. Okay, here's example number 2. And this is a classic example, guys, that you will see on your test. 100%. Okay, something like this with different numbers. It'll be, guys and girls and everyone else, eerily similar to what you see here in terms of the way it's formatted, just a different calculation set of numbers. Okay? Question for you. Do you see a right angle here anywhere? Check mark if you see a right angle, X if you don't. Come on, guys. Let's see some responses here on the participants panel. I see one X, and Kira says there is a right angle? All right. I'm not sure there's a right angle. Unless you subdivide the triangle. If you subdivide the triangle, you can make 2 triangles. One on the right-hand side and one on the left-hand side. Maybe that's what Kira was seeing. Thank you. If you think about this, if we make a right angle and we know what this theta angle is, if we do know this information and we know what this angle is, then we know what this angle is, right? We can make a triangle. And also, if we know what this angle is and we've split this down the middle, then we know what this angle is, right? Well, this angle would be 90 degrees. This angle here would be whatever this angle is plus 90 degrees. Take this angle, subtract those 2 things, you're going to get this angle here, whatever the remaining angle is over here, if we split this. So here it is, a traffic light weighing 122 newtons. Whoa, 120. When I say weighing, in your mind, you got to think mass times gravity, right? Mass times gravity. So if I know that it weighs 122 newtons, what's the mass? I know that force is equal to ma. Therefore, I could figure out the mass based on, right, taking the force and dividing it by gravity, right? So therefore, I could find the mass of this object if I want to. We know that this object is in equilibrium right now, right? So therefore, the tension of T3, right, is supporting the traffic light. We know that this is the case. So here's the question. The upper cables make an angle of theta 1 is equal to 37 degrees and theta 2 is equal to 53 degrees with the horizontal. These upper cables are not as strong as the vertical cable and will break if the tension in them exceeds 100 newtons. The tension in each cable has to be less than 100 newtons in order for this thing to stay in equilibrium. Does the traffic light remain hanging in this situation, or will one of the cables break? Okay, so how do you approach this problem? First, we conceptualize. We start drawing the stuff with different information that we have. 37 degrees, 53 degrees. Let us assume that the cables do not break and nothing is moving. Let's just assume that first. Okay, next, if nothing is moving, no part of the system is accelerating. And therefore, all the sum of all forces equate to 0, which means this object is in equilibrium. Similarly, the net force on the knot is 0. That means the knot, where is the center of mass, if you think about it, is not moving to the left, right, up, or down, which means the sum of all forces in this particular place here is 0. It's also modeled as a particle in equilibrium. The next thing we do is we draw a particle or a free body diagram, right? We construct a diagram of the forces acting on the traffic light and a free body diagram for the knot that holds the 3 cables together. Notice how it's drawn. And notice that even though we drew the object up above here, when we put this on an axis, what we get is the complementary angle. So 53 up here goes down into here. 37 up here goes down over here. Why? Well, geometry. We covered this in week 1, right? So 53 and 37. 53 goes here, 37 goes there, right? So now we have something we can start dealing with. And instead of it being a negative angle coming from the top, for example, I could have drawn this with the, the x-axis up here, which would make these angles negative. That is not convenient coordinate system. A convenient coordinate system is taking the x-axis and dropping it to the point, to this little knot here. That is a more convenient coordinate system. Okay? And then what I want to do is I want to draw the tensions down. So that's the tension wire. That is one force that we're going to draw. This is the sum of all forces that we're trying to figure out. And we know that this is another tension and this is a third tension. Okay? We want to find the tensions here. That's important. Next, we start summing up and splitting up each of the components of tension that we know about. So we can say that the sum of all forces on the y-axis must be 0 because T3 minus the force of gravity is 0. That means that the sum of all forces going this way must be 0. All right, therefore, the tension on the, I'm just going to zoom in here so you can see this. The tension, T1, the tension on cable number 1, is a negative T1 cos theta 1. And the tension on the y-axis, the y component of this tension, is T1 sine theta 1. Again, notice the relationship between y and sine, and x and cosine. This is something you're going to see over and over again in our examples, right? And the force, we can say, is of the tension on T2 is T2 cos theta 2, T2 sine theta 2, right? We could have used probably different symbols here instead of theta, right? T3, the x component, there's no x component. There's no force taking our T3 cable, that's the one that goes up and down, left or right. The only thing we have on the y component is negative Fg. Why? It's going in a negative direction in our drawing, in our diagram. Therefore, we can say that since we assume that the forces on the x-axis are in equilibrium, negative T1 cos theta 1 plus a positive T2 cos theta 2 is equal to 0. Similarly, the forces on the y-axis are T1 sine theta 1 plus T2 sine theta 2 plus a negative Fg. It all equals to 0. Why? Because we can say that the particle is in equilibrium. And why? What are these things mean? If you skip up back up again, this is T1. That's why it's negative. This is T2. That's why it's positive. T2 is up and to the right. T1 is up and to the left, which means on the x-axis it's negative. On the y-axis it's positive, which is what we're showing here. When we sub in, we want to put one tension in terms of another one. So we want to solve for an example T1. Okay? We can put one equation in terms of another one. Okay? One equation in terms of another one. In other words, if I know that the sum of all forces on the x-axis is 0, if I manipulate this equation and I say that, well, T2 cos theta is equal to, we take this whole thing, put it on the other side, with algebra, T1 cos theta, right? We know that these two forces are equal to 0, right? Then what we're going to get is, if I want to solve for T1, I can say that T1 is equal to T2 cos theta 2 over cos theta 1. That's what T1 would be. And if I know that, I can take any instance, I can take the first equation, T1 cos theta 1, again, T2 cos theta 2 over cos theta 1, and substitute it anytime we see T1. And when we do that, we now put things in terms of T2. Everything is T2. We're substituting, we have two equations and two unknowns, and we want to go to one equation and one unknown. That's what we want to go to, right? So in other words, when we go to the next one here, we can see that T1, in terms of T2 then, T2 is equal to T1 cos theta 1 over cos theta 2. You can put it that way too, right? And then once we know this, we can start substituting into equation 2, where we can say that T1 sine theta 1 plus T1 cos theta 1 over cos theta 2 times sine of theta 2 minus Fg is equal to 0. Then we solve for T1, and we rewrite the equation, so it's force of gravity on the top divided by sine theta 1 plus cos theta 1 tan theta 2, right? Why we get tan theta 2? Because if we get sine theta 2 over cos theta 2, that's tan theta 2. Sine over cosine is the tangent, according to trigonometry. That's an identity. Sine theta over cos theta is tangent. So that's the first one. So that's why we get tan theta 2 over here. And then we are left over with cos theta 1. Why is this over this? Because if I take the force of gravity and put it on the other side of the equation, over here, right? Then I'm left with, right, this is positive. And then what I want to do is I want to separate T1, right? As an example, we want to factor out T1. I'm factoring out T1 because notice that T1 is a common factor of both this term here and this term here. Okay, so if I factor out T1, then this will be equivalent to T1 times sine theta 1 plus cos theta 1 over cos theta 2 times sine theta 2. All right? And then when we divide everything, we're going to get something that looks like this when we move things around. Again, you need to use algebra for this to happen. Once we know this, we've isolated one variable. We can start subbing in what we know. We know the force of gravity, right? The force of gravity on an object, not gravity, but mg is what we're talking about here. That's equal to 122 newtons, right? We put that in there. And that's a little bit deceiving because you might want to put in, like, the way it's been written here is force of gravity. You're thinking about, 10 meters per second squared as an example, or whatever, 9.8 meters per second squared. But that's not the case. Force of gravity in this case is the mass times gravity, which is 122 newtons. So we sub that in, okay? And maybe this could have been written differently. And then what you want to do is substitute the things we know. Sine of 37, that's theta 1, plus cos of 37, that's theta 2, or sorry, that's cos of 37, theta 1, times tan of 53. And then you get an answer when you use your calculator to 73.4 newtons. So T1 then we know is 73.4 newtons. Now we sub it back into the other equation that we had before. So we say T2 then is we substitute T1 where it was. We put in 73.4 newtons. Look up here. So if I take 73.4 newtons and put it back wherever we see T1, 73.4 newtons, we can isolate for T2. Okay? Again, it doesn't matter which one you isolate, T1 or T2, but you want to get one equation in terms of the other one. Once we know that this is 73.4 newtons, we sub in the values that we know, 37 degrees and 53 degrees, and then we come up with a total of 97.4 newtons. So then, the test, are these two cables greater than 100 newtons, was the question, and the answer is no. However, T2 is close. T2 is close to the limit of what it can hold, okay, based on the angle that it's holding everything. But we can say that for now, the cables will not break, and unless there's another force exerted on it, this remains in equilibrium. These kinds of questions, guys, you need to practice. If you don't practice these questions, you will never remember how to do them. It takes practice, and you have to look at these things over and over again. All right, any questions around this before I move on to inclined planes? And the bird set on the wire. Exactly. Remember, and if the bird weighs, it's a quarter pound per newton. If the bird weighs, the big fat bird, that might be too much. It might set it off. There might be too much cable on the wire. Inclined planes. Again, we categorize a particle under a net force as an example. Forces acting on the object. Normal force acts on the perpendicular to the plane. Gravitational force acts straight up and down. Okay? So this is interesting. Normal force is perpendicular. If the plane is at an angle, the normal force is going at, which we call in 90 degrees or at 90-degree angles to the plane. Okay? Replace the force of gravity with its components and apply the model of particle under net force in the x direction and the particle in equilibrium across the y direction. Now, this is where, when we talk inclined planes, guys, where sometimes what happens is we have a swap of cosine and sine. Okay, when it comes to dealing with the y-axis or x-axis. You're going to see that in a second. Here's an example. So, if we were to put our x-axis and our y-axis like this, so again, we're using a convenient coordinate plane, then this is where, because we are rotating our coordinate system to match the angle of the inclined plane, that means that it's going to modify some of the ways we're looking at sine and cosine. Normally, I would say on the x-axis, it's cosine, and on the y-axis, it's sine. But not so in this case, because we've rotated our plane of our frame of reference. Now we have sine on the x-axis and cos on the y-axis, and this is only for inclined planes. In this case, the ones we've learned. So here's the question. The car mass m is on an IC driveway inclined at an angle theta, whatever that angle is. Find the acceleration of the car, assuming the driveway is frictionless. Well, we would rotate our coordinate plane this way, and we can look at it that this is the force of gravity. When we draw our free body diagram, we can say that this is the force of gravity. Notice the normal force would be counteracting, it's counteracted upon, right? Where we have the components of the normal force, right, are acting in a different direction. So we have mg cos theta is equivalent to the normal force. The normal force is mg cos theta, right? Mg sine theta is the force that we're moving across the plane with, this way, okay? And Fg is equal to the mass times gravity. So these are the forces that are acting on this thing. So we can take the force of gravity, which is acting down, and break it down into these component forces, mg sine theta and mg cos theta, right? Mg sine theta is the one we care about because mg cos theta is being counteracted upon by the normal force. So therefore we can find the force that's acting on an object. So here's the solution. We conceptualize, as an example, we draw the car, we put everything in its right place, we know what the gravity is, we draw it like we did. We know that the force of gravity is equal to mg, right? This one here, mass times gravity. That's the weight of the car, right? We know that. And we can start thinking about the sum of all forces. The sum of all forces across the x-axis then are mg sine theta, which is equal to the mass times acceleration across the x-axis, if we think about this. And we know that acceleration on the y-axis is in equilibrium because the car is not going to sink to the ground. Therefore, all we care about is acceleration across the x-axis, which is equal to g sine theta. We can break that down when we take mass out. We don't care about mass. Mass can cancel itself out, right? And all we're left with is acceleration on one side and g sine theta on the left side. So therefore, we have acceleration across the x-axis equal to g sine theta. So g being 10 meters per second, sine theta, if we knew the angle of the driveway, we would know the acceleration of the car. Who cares about the mass? Mass is irrelevant. All right, one block pushes another block problem. So I have one block of mass 1. Mass 1 we can say is greater than mass 2. They're placed in contact with each other, right, on a frictionless surface, horizontal, right? A constant horizontal force F is applied to M1. As shown, find the magnitude of the acceleration of the system. So again, we can consider the block as one system. We can add the two forces, M1 and M2, the masses together, M1 and M2. Once we add the masses together, we can consider this whole system as a point, or as an example, center of mass, and we can apply the same principles that we've done before. And I'm not going to go through this. You can look at that on your own. Pulleys are here too. I'm not going to talk about pulleys in these examples because, like I said before, they're there for your great entertainment. but for the most part, and they're great for physics learning, but not so great for game physics. Because how many times we use pulleys? Almost never in our games, right? If you're going to do that, then you have to do a little bit of research and find out how pulleys would work in a game. Here, we're not going to do that, so I'm not going to go through it. And you're not going to see pulleys on your test. Same thing with Atwood's machine. The idea that you have a pulley that with a cord and a tension. This is a great exercise. It's interesting, but it has nothing to do with what we're doing here in game physics. So I'm going to skip it. Forces of friction, however, are really important. And it says that when an object is in motion on a surface or through a viscous medium, by the way, a viscous medium, if you think about it, what that is, air is a viscous medium, right? So there will be resistance to the motion. This resistance is called the force of friction. There's two types of friction. And we can say that the coefficient of friction is mu. All right, mu is the coefficient of friction. There's two types. Notice that this one says Fs, friction or force of friction, S. This is the static force of friction. The static force of friction is less than or equal to the coefficient of friction, static, right? And times the normal force, okay? And the force of friction kinetic is equal to the force of the coefficient of kinetic friction times the normal force. That's what this thing means, okay? I'm just going to push this down here a little bit. So this equation relates to the magnitude of forces. They are not vector equations, okay? And we can think about that friction impedes motion. That's what it does. It provides additional resistance. The coefficient of friction depends on the surfaces in contact. The force of static friction is generally greater than the force of kinetic friction. In other words, if you can picture something that's at rest, remember, by Newton's first law, an object at rest tends to stay at rest, right? And if I want to push it, because we can think about mass as inertial mass, it's going to take a whole lot of energy or force to push a mass into acceleration, right? More than the force of kinetic friction when it's in motion. If a body's in motion, there's a lesser amount of force involved in keeping it in motion than getting it to go. Okay, it's actually true in psychology too. So here's an example of this, right? I have a free body diagram for this little drawing, and we can see that there's two types of friction: the force of static friction and the force of kinetic friction or motion, right? If I want to move an object, the force of static friction, if I'm moving in the right direction, if you look at this free body diagram, it's going to work in the opposite direction of the force that I'm applying, right? And it's going to be based on how much gravity I'm going to use, right? So example, the force of static friction is going to be equal to the, less than or equal to the coefficient of static friction times the force, the normal force. So the heavier an object is, then the more static friction you're going to have based on the coefficient of friction. It's directly related. Heavier the object, the more friction you're going to have. Similarly, you would take the heavy an object with a mass and a gravity and multiply the coefficient of kinetic friction to calculate how much resistance you're going to get across the surface. Okay, this is over time. So kinetic region. So example. There's two parts to the force, two different kinds of forces. The kinetic region is before an object starts to move, and then this object here is the kinetic region. So static region's here, kinetic region's here. So when I start moving. And notice that it switches. First we start off with static force of friction, and then we move to a kinetic force of friction. We have a table that we're going to see that is going to show us what that is. Okay, I'm just going to move to the next slide here. And this is the table. So we can see that some common coefficients of friction. Notice the mu static of rubber on concrete, 1. That means however big you are, the larger the mass, it's a 1-to-1 relationship. You're pushing against gravity here. Whereas when I'm moving, when I'm physically moving across, when I start moving, it's hard. But when I'm moving across rubber on concrete, it's not as hard. It's still quite hard, 0.8. As a factor, that's the coefficient of friction, times the mass times gravity. Mass and gravity is weight, right? So if it's a very massive object, then it would be hard to move. Steel on steel is less, and you can see as we get into things like ice on ice, that's like 0.1. So actually we reduce. So objects that are really, really heavy, they still have a bit, they take a little bit to get going, but then when they're going, oh my gosh, it's like they're weightless across the surface, right? And I say weightless because it's mass times gravity. So when we talk about friction in Newton's laws problems, the friction force is simply included in the sum of all forces in Newton's laws. In other words, we take the friction force into effect. We subtract the forces, right? So here's the same example where we say, okay, suppose a block is placed on a rough surface inclined on, relative to the horizontal as this, right? And before we didn't care because it was a frictionless driveway. Now we have a force of static friction that points in the opposite direction as the mg sine theta, right? We conceptualize, we write things down as before, and what we get to is this. The sum of all forces across the x-axis is equal to mg sine theta, which is this positive number down here, it's across the x-axis, minus, in the opposite direction, the force of static friction, which can be calculated as the force of gravity, mg, times the coefficient of static friction, whatever that is. And we don't care about the force of static friction across the y-axis because there's nothing that's acting on the y-axis when it comes to friction in this case. So therefore, we can re-equate things. Once we move these around, you can get, if you want to calculate the force of static friction, you can say that once you move it around, that force of static friction is equal to mg sine theta, right? Move this on this side, which is equal to the normal force, because the normal force is part of force of static friction, over cos theta, sine theta. So we can say that the force of static friction then is the normal force times tan theta. And this is a great little equation, guys, because this is the same for any kind of inclined plane. Okay? And when we know that, if we know that the coefficient of static friction times the normal force is equal to the normal force times tan theta, then we can say that the coefficient of static friction is equal to tan theta, which is interesting. You can actually calculate the coefficient of static friction. So here's friction example 2. A hockey puck on a frozen pond is given an initial speed of 20 meters per second. Okay, cool. This way. If the puck always remains on the ice and slides 115 meters before coming to rest, determine the coefficient of kinetic friction between the puck and the ice. That means it's already moving. We don't have to think about the coefficient of static friction. It's already moving, right? So we start categorizing it, we draw a free body diagram, and we start thinking of something like this. The sum of all forces across the x-axis are equal to a negative force of kinetic friction is equal to mass times acceleration on the x-axis, right? And on the y-axis, we can say that it's an equilibrium. We don't care about the y-axis again, right? So then we only care about the x-axis. We can say that a negative coefficient of static friction, kinetic friction times normal force, which is what it is equal to, if we break down what this is on the right-hand side, a negative coefficient of static kinetic friction times mg, which is the normal force is equal to mass times gravity anyway, right? And that's equal to mass times acceleration. Force is equal to mass times acceleration. This is by Newton's second law, right? Then we can say that the acceleration on the x-axis is equal to a negative coefficient of kinetic friction times gravity. And if you move things around, you can figure out that the force, the coefficient of kinetic friction is velocity across the x-axis initial squared over 2 times gravity times on the x-axis times force. This is what this is here. And if you use this equation here for anything, when you want to find out the coefficient of kinetic friction across a surface like this, you can use this equation because it's going to be the same. And now you sub in the initial velocity. We know the initial velocity is what we're getting at, because we're saying the initial velocity on the x-axis squared, plus 2 times the acceleration, right? Where do we get this from? This comes from our kinetic formulas from motion in 2 dimensions. That's where this is coming from. And then we're going to get this, where we're subbing in the velocity. The initial velocity is 20 meters per second squared over the numbers that we know. So we can say that the coefficient of kinetic friction here for this piece of ice is 0.177. Notice that there is no unit of measure here, because we're talking about the coefficient of kinetic friction. We're not talking about any kind of force here at all. All right. Again, we're probably not going to do something that goes like this. So I'm not talking about the friction with pulleys. It's nice for your information, but not really relevant for us. Now, from here down, there are some example questions that I'd like you to try and practice on, right? For the test. These are questions that you might see on the test. Every PowerPoint that I've given you has example questions that you might see on the question. They'll be eerily similar. So if you figure these out in class, in tutorial, as an example, in your lab, or you figured them out on your own, this would be great for how it's going to work for your test, midterm. Let's think about this. A woman weighs 120 pounds. Okay? Stop. What do we know about her weight in newtons and her mass in kilograms? How do we figure this out? Can someone help me out with this one? This is going to be on your test, something like this. I know it's a silly question, but what is her mass in kilograms? How do I find her mass in kilograms? Quarter pounders? Yeah, we can look at quarter pounders for sure, right? So that's 1 newton is a quarter pound. So if I divide this or multiply this by 2.25, let's try that. Let's see if that makes any sense. So I'll bring up my calculator for a second, and I'll say it's approximately 0.25 pounds per newton, right? And if I multiply that by 120, we're looking at 30 newtons is what we're estimating. Okay, let's see if that makes sense, right? So 30 newtons, that's force. Force is equal to ma, right? And if I know that this is force, mass times acceleration, if I want to find my mass, then I want to take my total force divided by my gravity. So 30 divided by 9.8. We can estimate her mass using that quarter pounder theory, at approximately 3 kilograms. Does that make sense? Sorry. Yes, 3 kilograms of mass. So if you think it doesn't make sense, right? 0.25 is the quarter pound for every newton of force. So if it's 120 pounds, then it's, as an example, then how many newtons of force is it? Okay, so, and actually maybe it would be 4 times this instead of 120, because this is a bunch of quarter pounds making up this thing. So actually it's the other way around. It's actually bigger. If we're going to estimate it again, it's 120 times 4, right? Which is equal to 480 newtons. Let's see if that makes any sense. And then divide that by 9.8, which is roughly equal to 48 kilograms, right? That makes more sense than 3 kilograms, if that was the case. But let's use force is equal to ma, right, for this one, right? So if we know that this is 120 pounds, we can also convert this into kilograms. That's one way of doing it. What is her weight in newtons, right? And her mass in kilograms. Or her mass in kilograms, as an example, we divide this by 2.2. That's one way of doing it. We know that her pounds divided by 2.2, right, is roughly something like 54. We're close with what we said, 2.2 something, right? So that's approximately her mass in kilograms. Her weight in newtons, though, is, that it's mass times gravity, right? Mass times gravity is her weight in newtons, right? So if this is her mass, let's just suppose, and mass times gravity, but then we want to find her weight in newtons, so multiplied by gravity, 9.8, is roughly 534 newtons, if that was her mass, 54 kilograms. Yes. 1 pound is approximately, you said 1 pound is 4.45? Yeah, that's why I said approximately quarter pound. Yeah. It works out to be the same if you think about what we talked about. All right, next one. A car with a mass of 850 kilograms is moving to the right at a constant speed of 1.44 meters per second, right? Okay. What is the total force on the car? Okay. What is the total force on the car if it is moving to the left? So here's something to note. I'm moving at a constant speed, right? Am I accelerating? If I'm not accelerating, then there's no force. The force is 0 if there's no acceleration. Remember that? It doesn't matter. These things that they're telling you is not important. Right? The total force on the car, if I'm not accelerating, there's no force. Force is equal to ma. Okay? The force exerted by the wind on the sails of a sailboat is 390 newtons. Okay? North. The water exerts a force of 180 newtons east. So I guess I'm looking at it from a top-down perspective, right? If the boat, including its crew, has a mass of 270 kilograms, what are the magnitude and direction of its acceleration? How would you approach this problem? What you do is you create a free body diagram, right? So you'd sit there and say, okay, so 390 newtons north. So I would draw an arrow for my free body diagram. Let's draw a big fat arrow, right? I want to draw an arrow the other way around. The other way around. Where's my arrows? I want an up arrow. This one. I want to draw a big fat arrow going up, right? That is 390 newtons, right? And then I would draw another arrow going east. So where is east, cardinal direction wise, right? It's north, south, east, west, right? So east is here. So I have a force this way, and if you think about east, right? So let's look at, I'm going to insert another, where the heck is it? Another object. Why am I suffering here? Let's go back to this. Yeah, so I mean, I'm just drawing these objects. So I'm going to have a smaller arrow this way, okay? So I'm drawing the diagram first. That's the first thing I'm going to do, right? And the reason why I want to draw the diagram, the free body diagram, is because that's what we do first. We draw the free body diagram first, right? And we start labeling the free body diagram. So we sit there and go, okay, I want to put the numbers where they're supposed to be. This should be 180 newtons to the east. That's the water. Now this is, don't be fooled with northeast. It's 180 newtons east, right? And we want to put the units. And then we take this thing and we want to put the units up here. All right, so this is 390. Guys, and it says the water exerts a force of this and the boat, blah, blah, and the mass, we know the mass is 270 kilograms. What are the magnitude and direction of its acceleration? We know there's acceleration because we have force. Force and acceleration are directly proportional to each other, right? So we have an acceleration across the x-axis and we have acceleration across the y-axis, right? What could I do? What is it means? Pythagorean theorem for sure, right? There's no coefficient of friction, okay? Kira, none, right? We would draw an arrow that goes like this, or a nice way to do it is you'd move this over here, right? You could do this, and then you can draw an arrow. I'm not sure if I can do that, but I'll try, right? Let's draw this arrow. We'll draw an arrow that goes like, no, it's not going to work for me. I'm going to have to rotate the arrow. Like so. So this is the magnitude and direction of these two things combined. We know that this is an angle, right? What we want to do is we have 180 and 390. We know that x squared, c is equal to c squared is equal to a squared plus b squared. So therefore, what would be this, the amount of newtons in this direction? And what we would try and solve the triangle is what we would do. That's the best way to do it. Do we care about the 270 kilograms? If the boat, including its crew, has a mass of 270 kilograms, what are the magnitude and direction of its acceleration? Do we care? And the answer is yeah, we do, because then we can break it down, right? Because we're looking at it from a top-down perspective. Because the water is keeping the boat afloat, we don't care about direction and towards the water. That's not important. All we care about is a top-down diagram like this. So this is definitely a way you can handle it, by thinking about the magnitude and direction, where we don't care about the kilograms at all. Okay? So, but we want to find acceleration later. This is where this is what we're looking at. If we get acceleration, right? If we have forces here, and we have this, then we can find acceleration. That's the final thing we do. So first we find the force here, resultant force, right? And then we can use F is equal to ma to figure out its acceleration if we have the mass. Okay? And I think I'm going to leave the rest to you. There's two more that I'd like you to look at. Oh, look at this one. By the way, guys, this is going to be eerily similar. This question here is eerily similar on the test. Okay? Like I said, doesn't this look like the lamp question? You're going to see something just like this on the test. Okay, guys, that's all I have for you today. I'm going to stop recording this right now. I'm going to stop, and I'm going to we're going to talk about some questions you might have about your about anything we've talked about. So let me stop recording right now, and I'll go to questions.